So your metal plates.
Okay, we should start. So welcome to week 3 of advanced cognitive modeling. It's nice to see you survived so far. Whoops. So I have uploaded the slides and linked them, right? You found them. There's a ton load of slides, not because we need to cover 100 slides today, but because the argument is kind of one, and I was rebuilding the slides. So, and I've actually just rewrote those up to the point where I think we're going to get today. So don't worry that there are too many. We're not going to cover them all today. So far, we have discussed the conceptual framework of cognitive modeling, what the heck we're doing here. We have formalized models of agents playing the matching pennies, where the mechanisms that are not directly observable, but could generate the behavior that we observe. I've seen at least 4 of your group assignments, so I know you're doing that. If you haven't submitted yet, you can still manage it because I haven't finished giving feedback to everybody. So we have simulated the behavior generated by our models because the implications of the equations and model are not always obvious, and because that gives us data that we can use from today on to actually fit the inferential models, right? Before we even look at empirical data. So next steps. Before we go into that, do you have questions on the process so far? On the contents, all is good. Yes?
We stumbled on some more technical questions about reinforcement implementation.
Yep. So I'm covering a bit of reinforcement learning in a bit, and then at that point will be the time to ask questions. Yes, for that about that. But this is good to know. On the assignment, everything went well. It made sense. Good. Have you read the notes? I rewrote completely the notes on the mathematical models of underlying the matching pennies. Any comments? Yes.
We were thinking about the estimated value versus predicted value. And it's really also related to the model specifically for reinforcement learning.
For reinforcement learning, yeah.
Just terminology.
Yeah. So I think that in strict statistical terms, you could separate them, but for our perspective, it's the same, right? So what is the expected value? It's the value that you estimated you would get if you played right. Yeah. Okay, good. Then we're going to do a little bit of reinforcement learning, just because I discussing with some of you last week, there were some questions and doubts, and now more are coming, so that's a good thing. And then we're going to start the process of going from the data that you generated so far to models that make inferences on the data. I was preparing slides going straight into how we fit an inferential model of reinforcement learning, but I think it's too early because it was getting too complex. We're going to start with the simpler models. And just restating that if you check the readings for this week, there's actually much more about Stan than we can cover in class, right? Because I'm going to give you like all the basics that you need to be able to write Stan, but that gives you a broader perspective. So it's a good idea to have a look at that. Yeah, and then there's course notes. Okay, so reinforcement learning parentheses. Before we go and build inferential models, I wanted to talk a bit more about reinforcement learning because it's one of the first complex models that we are meeting. Actually, I think I already discussed this. And this. But so we have two key parameters, right? We have a learning rate, which is the rate at which the model adjusts its expectations to the word, right? When the model gets feedback, it takes the difference between the feedback and their expectation, and then adjusts the expectation accordingly in a way that's moderated by the learning rate. If it has a high learning rate, it adjusts it almost as much as the feedback is saying, otherwise less. So higher learning rate, faster learning, but also less memory, right? Because if you're waiting a lot, the incoming input, right, automatically you put relatively less weight on the past. These makes the expected value swing independently of previous experience. If you have a lower learning rate, you have a slower learning, but you're also less dependent on the noise. To the point that a lot of learning algorithms these days, they actually try to combine the properties of both. They say at start, you learn a lot because you don't have much to go on. But as the game or the task progresses, then we decrease the learning rate so that you're only swayed if you consistently break your expectations, right? This is called annealing, for instance, and it's very studied in physics because it's the behavior of glass that at high temperature moves a lot and then it slows down, right? But it's all over the place. The other parameter of the algorithm, reinforcement learning algorithm, is not on the estimation side, but it's on the decision side. It's the temperature, right, or tau. And that determines how determined the choice is by the estimation. With a high temperature, what you get is that the choice is often not what you would expect from the expectation, right? So the expectation tells you play right. But if you have a high temperature, the model is also often going to pick left. If you have, sorry, it's the, oh, what's happening here? You can do it. Yes. Okay. If you have a low temperature, and I know that says something slightly different, but give me a second. If you have a low temperature, your choice, so even if your model is saying it's only slightly more than chance that you should expect right to yield more value, then you automatically go for right. Tau works the opposite. Like lower tau means that it's more stochastic, there's more exploration, and higher tau, it means that it's more deterministic because the models tend to use inverse temperature. Okay. Now, what I had told you I would do, maybe I'll just temporarily turn off the light, but is that I would dedicate a little more time on why the specific formula of reinforcement learning, in particular the update rule, actually gives rise to exponential decay. Because it's that sort of things that I always read, right? And then it makes sense to me, and then I forget it. And then the only way for me to retain these is to go through the math, right? So if you remember, what's the formula of the update is that the expected value at time t is given by the expected value at time t minus 1 plus the learning rate multiplied by the predictive error, which is the feedback minus, and I should have written v at t minus 1, right? Value. Yes.
You noticed in our study group when doing the assignment,
Yeah.
the feedback was written as the feedback current trial, whereas elsewhere in notes last semester and other places whilst researching, it said it was feedback from the previous trial.
So it's the feedback for these value, right? So it's the feedback for the trial in which you played according to this, right? Yeah, so it's feedback at t minus 1. Right? Yeah. You can sometimes what people do is that they say t and then this one is t plus 1, and that's where things get confused.
I think in your notes you bring this feedback for t, but it's still the t rather than t plus 1.
Yeah, okay. Yeah, that's probably because in the code, the VT at -1 is fully updated after you get the feedback at t minus 1, and then it gets passed to the next trial. But yes, it's confusing. I'll have a second look to check to make sure I clarify that. Yes. So let's imagine that we have a series of outcomes, 1, 0, 0, 0, because it makes the calculations easier, right? And start with an expected value of playing 0 equals 0. Right. So we have that at t equal 1, we have that the value, expected value of playing 0. No, I think it's expected value of playing 1 is determined. No, so yes, the expected value of playing 0 at time 1 is given by the previous expected value, which was 0, plus the learning rate multiplied by the feedback. We got 1, right? Minus the expected value, which was 0. And so if we simplify this, we get that the expected value of playing 0 at times 1 is alpha. Because 0 goes away, this 0 goes away, so we have that v of playing 0 at time 1 is equal to alpha times 1. Then we go at time 2. Say that the expected value at the end of trial 2 is given by alpha times, so alpha is this, right? The previous expected value, plus learning rate times 0 minus alpha, because alpha is the currently expected value. And that gives us, so this would be alpha squared. So alpha times 0 is 0. Alpha times minus alpha is minus alpha squared. And the exponential went away when I copied and pasted stuff. But so we have that the expected value of playing 0 at time 2 is given by alpha minus alpha squared, which, if you extract an alpha, becomes alpha times 1 minus alpha. Does it make sense? Then we use these to replace the expected value, right? Because it's the new expected value. So at time 3, we have that these expected value has to be summed to learning rate times 0, feedback, minus the expected value, this thing. We can solve from that, and then we get that the result is alpha times 1 minus alpha to the power of 2. As we go at time 4, right, we repeat the same operation, and we get that the result is alpha times 1 minus alpha to the power of 3. And we can start to see a pattern. Right? So we see that the exponent is increasing linearly, which implies an exponential increase. Right? So what we have is that the influence of that initial outcome, 1, is being multiplied by 1 minus alpha at each step. So we have that the impact at the beginning gets multiplied by this to an increasing power, right? So you always have alpha, which was how much you change your idea after seeing a success or a feedback of 1. and it get multiplied by 0 to 1, so a decimal number, right? Which is lower than 1 and gets increasingly exponentiated, meaning that it gets smaller and smaller. So the impact of that initial alpha gets at every step smaller of an extra exponent. Yes? Yeah, yeah, exactly. So you can run it with, so this is the simplest possible version. You can run it with any sort of outcomes, but then it becomes harder to see what's the impact of the first choice because you reinforce it every now and then. So in a sense, the influence of a given feedback in time is given by alpha times 1 minus alpha to the power of k, with k being the distance between the current moment and the previous moment. And if that doesn't make super intuitive sense, we can also plot it and see how with different learning rates, the impact that we have at time t of the current feedback as we move away from time t decreases at different rates with different learning rate. If we have a high learning rate, remember that it's 1 minus alpha that determines the decay. It goes down very fast. If we have lower learning rates, it's not impacting us as much at the beginning, but it's decaying slower. Does that make sense? Yes.
Would you mind just stating again what it is?
K is the distance from, so it's if we are, how many steps we are from that specific feedback that we got.
Yeah.
So that at one step, the distance is basically going to be, exponentiated at 1. So here it could be 0.1. But if we're at step 2, this would be exponentiated by 2, and 0.1 would become 0.01, which is a very strong decay. Good. So if we want to simulate data with that, right, here is an example of a function where I expanded it to separately calculate the expected value of both choices, just to show you how it is. They're absolutely connected to each other because here we have a binomial choice. We have that the function of value update, which is that formula, takes as input the value at this given point in time, the alpha, the choice, and the feedback. Those are the things that it needs to run the update rule. Then it calculates the predictive error, feedback minus the value. And then it says the expected value of the first choice is the value of the first choice at the current time plus alpha times, and then we 1 minus choice times the feedback minus value. I could have actually simplified it with the other one. Oh yeah, oh no, sorry, I couldn't have simplified. So usually we would have that it's alpha times feedback minus value. But here, since we're separately updating the value of the two choices, we are saying there should be an update when choice is, so in this case, when choice is 0, this becomes 1. So we get this update. When choice is 1, so the second possible choice, because they're in order 0 and 1, this becomes 0, and there is no update on the expected value of that choice. This is to describe situations in which you have to pick, right? Are you going to hunting for rabbits or for deer, right? Are you pulling the red lever or the green lever? And these two actions might give you very different payoffs, but they're not related to each other. Then our new updated value is a vector with the two values. and it's spat out. Once we have the updated value, then we can run the softmax, and at least a simple version of the softmax requires one value. So we can say that our relative value of picking 1 over 0, or picking the second choice over picking the first choice, is the value of the second choice minus the value of the first choice. And then we can run the very traditional function of the submax, which takes the relative value and the temperature, or inverse temperature, and it calculates the outcome as 1 divided 1 plus the exponentiated version of minus tau times x. And then what we can do is we can start simulating data from this. And to make the plot simpler, what I do is that the algorithm always picks 1, so that we can see how the expected value of 1 changes as a function of different feedback from the environment, which makes the plot clearer. Because if the agent was to play sometimes 0, sometimes 1, then it would be hard to disentangle the effect on the expected value of playing 0 or playing 1. And we can see here that for the red line, we have, oh yeah, sorry. This is the red line is the feedback that the model is getting. And the blue one is the update in the expected value. So once the algorithm gets a negative feedback, right? They picked 1, they picked the right hand, and the penny was hidden in the left hand. The feedback goes to -1, and we see that the value very quickly is following, right? At 1 step of distance. When the feedback goes up to 1, then again, the algorithm updates the expected value to be in favor of a choice of 1. When we manipulate alpha, we have here on the x-axis the number of trial, on the y-axis the previous feedback or the expected value, right? However you want to conceptualize it, it's the same. And we have that in red is the feedback as before. In purple is an algorithm that has a learning rate of 9. And you can see that the purple one is the one that's following the feedback the closest, and it's getting up and down very quickly. In blue is a learning rate of 0.5, and you can see that it's slower in uptake than the high learning rate. And it never really goes all the way down in this specific case. It would take way more. Yes?
So the green one here would actually never switch. It would never pick in else if it was deterministic.
Well, in this specific sequence, it wouldn't. It would always pick 1.
Yeah.
But if there was a longer sequence of zeros,
Okay.
or feedbacks of -1, right, it would eventually go below. Yes. It's just very slow. Good. Then just for the fun of it, and I don't want to spend excessive time on that, but we can put it to play against biases of biased agent with a bias of 0.75. And then we can see with different values of learning rate, how the model would be doing, and with different values of temperature, how the model would be doing. And to make things more complex, but perhaps more interpretable, eventually, I split the panels here by tau. And then we have the color is the learning rate. And you can see that with a very high temperature, the separation in performance between the different learning rates is very clear, right? They always respect the same ranking. The one with this one is, let me think. This is the highest. So the one with the lowest learning rate is actually performing best. As you increase the learning rate, the performance is decaying a bit. Yes.
I'm a little confused about temperature and inverse temperature.
Yes.
So
50.
plus we have.
So let's start only on the left. Yeah. So we have that each of the panels is a different value of tau, which is the inverse temperature.
Inverse temperature.
Yes.
So highest was
Exactly. And so once we have basically no noise in the decision process, we can see a very ordinal effect of learning rates, which makes the impact of learning rate very clear. It says if the opponent is noisy, right? It's a biased opponent that picks 75% in one direction and 25 in the other without any other discernible pattern, right? All these models are converging towards 0.75, but the low learning is converging better, faster, and it's getting to the exact value eventually, because it's not swayed by the occasional choice towards the left end or zero. Faster learning rates have a harder time getting there. They get a lower performance because every time that there is a left hand, they move their expectations towards the left. Yes?
If you have enough trials, will it ever matter? Like if you put 1,000 trials, will they all land at some point?
With a very, very high, yes. But you still get slightly less. I think you still get a slightly less lower performance because it's going to change, while the other ones are high enough and they never get below the threshold. While if you have a high learning rate, even after 1 million trials, as soon as the other picks left, you're going to be swayed more. While the optimal strategy is to always pick one. But that's not what those models are doing. They're going to say, oh, maybe now it's the time for left, right? And the low learning rate is never going to do that. So correcting my initial answer, even after 10 million or 1 billion trials, you'll still have a hierarchical difference in overall performance. As we decrease the tau, that is, we increase the temperature. Don't you hate machine learning people for messing this up? Then what we have is that the pattern gets way more confused, right? Because the choice is not as deterministic. So we would need to run 1,000 agents to get these neat patterns. So we could average away from the random choices. And still, we would probably get more variance in the position of these ones. The panel on the right is a thing that I often do when I'm exploring models, is exactly the same data as the panel in the left, but I'm stratifying it differently. So I'm separating, rather, each panel is a different learning rate, and the colors in the panels are different taus. So we can see the impact of tau on performance on a level of learning rate by level of learning rate. So what we can see, and it's not absolutely clear, but it's that, let me see how to tackle it. So if you go, which part I should start? I think, so that if you go at the extremes, so low learning rates or high learning rates, you see that the performance is squeezed and that the temperature, low temperature, is pretty constant, while as you increase, why did I write temperature? I should have written tau. And then as you increase the tau, that is, you decrease the temperature, things are getting very messy. Because if you learn a lot, you're swayed by the noisy behavior of the biased agent, and the temperature is not moving you away from that. And yeah, I think that's more or less that. But this is more messy, right? So this is the one where it's clearer to get a lesson. That one, if I want to see how with different learning rates, the impact of temperature changes, is just telling me that there's a lot of noise, right? It's really hard to sort of make a systematic claim there. Good. Are there questions on the reinforcement learning? I think you had some from your assignment.
I think they did on the indexing we were also confused about. But
Yeah.
The name expected value. I think it's a number. Oh yeah. You write in the course notes last time I checked that the expected value or the estimated value is probability.
If we have a feedback of 0 or 1, yes.
This specific case.
Yes. Yes.
But normally used for software.
Exactly. Yeah.
Let's get up.
Yes.
Yes, just a question about the plot of the right.
Yes.
It's just that in my division, I think that if the environment is more volatile, then a higher learning rate would actually be better. But maybe it's not. I couldn't really tell now if that was the case.
So here we're not manipulating the environment.
I also, okay, no, maybe this is
Yeah. So because I think your intuition is right. So if the environment is changing, you want to change your expected value just as quickly. But here it's actually the noisiness of the choice. Right.
Yeah.
And the higher the tau, the more deterministic the choice is. So that's what we're plotting. Martin, did you have a hand? Okay. Yes.
We were wondering, and I can't remember what I said about it, but
Yeah.
I think when he was talking about how it can be a bad idea to maybe model choices 1 and 0, and to like index it as 1 and 2. Do you know, like?
So often the softmax implementations, they take categorical outcomes so that you can have 3 different choices or 4 different choices. And so if you model it as a 0 and 1, they don't get it because they want the number of the ordinal number of the category or just the index of the category. So you have 1, 2, 3, 4. That's just depending on the implementation that you have.
Okay, so it's not gonna.
No, exactly. Well, you could do it.
Yeah.
There are implementation of softmax that only want that. When we build inferential models, it's the difference between picking a Bernoulli as a way of modeling the choice or picking a categorical, like a multinomial distribution. And then if you pick a categorical, as we will do when we do categorization, you need to use 1 and 2, because otherwise it gives you an error. But if you pick the Bernoulli, then you can use 0 and 1. And you shouldn't use 1 and 2 because otherwise you get an error. So the 1 and 2 is more scalable to more than 2 choices. But when you only have 2 hands, then it doesn't really matter. Yeah. Okay. So now we go to the part where we can start figuring out how to build a stand model from the R code that you build. So we're going to pick a few models that we're going to discuss. First, the biased agent. I should change the name. It's not named random bias anymore. That has 1 parameter, right? It has, that's rate. And it has a choice rule, which is R binomial. So sampling for 1 trial, 1 time, given a rate of rate at 0 or 1, right? Then we have the noisy random bias, which we've seen before, that has two parameters, the rate and the noise, and it has the choice rule that it does the same thing as before, but then it also samples from a binomial with noise as its theta or rate. If once comes up, it picks a completely random choice. Then we have the probabilistic win, stay, and lose shift. That has two parameters, right? The probability of staying when you win and the probability of shifting when you lose. How do we turn that into a model? I know some of you went for the probabilistic win, stay, lose, shift. So how would you write the formula of that model? And somebody took away again the markers, but that's not a problem. Yes, anybody? But remember that what you have in each trial is your choice, right? And the feedback that you get from your choice. Oh, thanks. Remind me to give it back. Yes. And the formula inside is going to have two parameters. Somebody had a raised hand. Nope. So how do we connect the previous choice and the feedback to a probability of staying and a probability of living when losing in a mathematical formulation? Yes.
So I would say that. So you said your probabilities now are they for when you win or for when you lose?
This is the probability of staying when you're winning.
Yeah.
And this is the probability of living when you're losing. Yeah.
Yeah. So I don't know. I would say that, but like if the feedback was equal to the choice, you would say the probability you would simply do like the bias agent, like it's probability.
Yeah, but actually I don't want an if else. I want a mathematical formula that gives me everything, because if else are very computationally costly. If we can actually write one mathematical equation that gets rid of the if else, the model is going to be much faster. And it's good for your thinking. Yes.
Something like you have an indicator variable, whether you want or not.
Yes.
By state probability, and then you add that to 1 minus the leap probability times 1 minus bit win, and then that's your state probability.
Yes.
Yeah.
So writing it, one step at a time, what we want is a variable that we can put here, which it's 0 if we lost, and it has a value if we won, right? Now, our outcome is always the choice, right? So it's a 0 or a 1. So what we want is that if we won, this value should be positive. So if we won and if we won and we played right, we want this value to be positive because we want the choice of right to increase. If instead we won and the choice was left, then we want a minus, because that is going to decrease our probability of picking 1, right? Because we're won by playing left, and therefore we want to stay on the left. We don't want to go to the right. Does that make sense? And here we want something similar. We want a variable that is 0 if we won, and it's positive if we lost and we were playing left, right? And negative if we lost and we were playing right. Because we want to leave, right? We want to shift. So if we played left, we should increase the probability of playing right. If we played right, we want to decrease the probability of playing right. Does that make sense? Yes?
I guess I'm wondering, maybe because I don't really get it.
Yeah.
But isn't that sort of the same as reinforcement learning with the learning rate less?
Yeah, it is. So except that now we're separating the probability of staying from the probability of shifting. Yes. And we don't have the softmax, for instance. We could put it in, right? But I'm starting with these 3 more simple models so that we can build all the way up there. Yes. But it does. So basically it's saying how much should you follow the last feedback. The other difference is that these does not keep memory beyond a trial of 1. While the other one still has the previous expected value that's sort of inertially pushing it. So even if you have a very low stay P, which would correspond to a low learning rate, right? In the reinforcement learning, you can still start with a very high probability of picking right, while here it's going to stay at random, right? Close to random.
I guess we're not updating.
Exactly. So it's a very simplistic version of the reinforcement learning without a memory. Yes. Yeah.
Just with the C, you were returning one from there.
Yeah.
Like nudging, but nudges one from the other, or is it like the person choose 0?
Perfect question. So now I was sort of glistening on that to see when we would get there, but this is a binomial choice, right? And here we're talking about kind of probabilities of a sort, right? And so here we probably want to have a rate of choice equal 1, right? Which is equal to this thing. And then we will have some sort of decision rule, which will turn the rate into a binomial choice. Does this start to sound familiar? Did you ever run something like that? Like you have an equation with some predictor, which outputs a probability, which then turns into a decision? What is this? Yes.
Sounds like less fun. You just a regression.
So logistic regression, yeah. With, depending on the link, it could be a probit regression, it could be a logistic regression, but it's a binomial regression of a sort. Yes. Yeah.
And maybe this was already said. I'm not sure, but why do we need both? But stay and leave.
Because now we're allowing these things to be different. So I might have a stay probability of 0.6. where I'm more likely to stay after I win, but not that much.
Okay, I understand.
And here we could have a live probability of 0.9.
Yeah, okay.
Yes.
I'm a little confused by the number of indicators here. So we have the indicator for windows.
Well, that's what we need to figure out. Yes, we're not done.
Yeah.
But I was sort of taking the drift because what about this, right? Yeah. So basically, what we're trying to do in this specific case is we realize that this can be a logistic regression kind of thing. And if we run all this if and else, the code gets complicated, the sampler, it's slower, and we want to start to learn mathematically so that we can turn a lot of these models into elegant equations. And Martin had, I think, given a correct solution, but I wanted to go through things step by step. So one possibility would be that we simply create what do we call it? An index that would be a win state. And we just take all of the feedbacks and of the choices, right? Even before we run the model, and we create a new vector that says if loss 0, if 1 and right, the scale doesn't matter, let's say +1. If 1 and left, we could say -1. And as Martin was suggesting, we don't even need to have it as an if else, but we can create a small equation, which now I forgot, Martin, which one was it? I can calculate it after and then write it up. All right. And then we do the same here with 0, well, yeah, +1 and -1 in these different conditions. Then we have our equation of, yes?
So would you just mind restating the win state 0 +1 -1?
Yes. So the idea is we want a predictor variable, a lost state, that is like cancels out this probability if we lost. So this is not relevant. So this part should not update, should not define our choice. But if we won, it should update or should change our choice. And here we have two possibilities. If we played right and won, we want to stay with right. So we want to increase the probability of playing right. And that's where we can write +1. If we lost and played left, we want to, sorry, if we won and played left, we want to increase the probability of playing left, which means decreasing the probability of playing right. And therefore, we call it -1. For the lost state, we have something similar, right? We have a 0 when we want leave P not to matter for our choice because we haven't lost. If we lost, then we want an absolute value different from 0. But if we played right and we lost, right, we want to shift. So we give it a negative value, -1, because we want to decrease the probability of playing right. If instead we lost and played right, we want to move away from right. Did I say the opposite? I just got lost. But if we lost and played right, we want to decrease the probability of playing right, so it should be negative, and before it should be positive. That's where I got confused. And so what we can do is we can simply create these vectors from the previous choice and the feedback. And then we have our equation, which is the stay probability, and here I should call it the shift probability. And the shift probability, which affect the choice only, the stay probability only when win state is different from 0, only when we won, and shift probability only when we won, so the lost state is 0. Shift probability only when we lost, and therefore the loss probability is different from 0. So this gives you an equation of the model. But since we said that we know this is a logistic regression, right, of sort, what's the scale of these parameters? So we have been conceptualizing them as probabilities, but say that here we get a -1. if this is a probability of 0.6, we get minus 0.6. And a rate can only be 0 to 1. So how do we deal with the fact that we've kept thinking in probabilities, but staying in this space of 0 to 1 for this equation makes it really difficult to stay in the space of 0 to 1 for the outcome? Yes.
I think we can log out set and then we
Yes.
the inverse logic.
Yes, perfect. So what we have is that when we want to have an outcome that's bound between 0 and 1, we can say that whatever mathematical process generates it should be in log odds, because every time that we have log odds is an unlimited space. It goes from minus infinite to plus infinite. But no matter these values, once we pass it through the inverse logit, it goes back to the 0 to 1 probability. So it can vary as much as it wants. We don't need to worry about that, as long as at the end we pass it through the inverse logit. Right. So here it would be the inverse logit of that. Right. Whatever comes out of the equation, we pass it through the inverse logit and we get a probability back. That's the probability of picking right. Yes. Oh, there was a hand. Yeah.
Yeah, it was. Do we need to do anything in the other part of the equation to make it log us?
No, that's the beauty of things, because now what we have is that, this is pushing us in the positive space towards right. This is pushing us in the negative space towards left. So it just works. Well, so that's the beauty of log odds, is that you don't need to worry about what happens in that space, how things add up together, because you're going to convert them to 0 to 1 at the end, instead of having to put a lot of checks and figuring out, we need to make sure that these things will never multiply to something below 0 and never multiply to something above 1.
So it's only their relative difference that matters.
Yeah.
Yeah. Okay.
Good. So let me see what was here. Yes. Yes. Okay. Let's take a 10 minutes break and then we'll start playing with that. We'll keep on playing with that. It's a learning algorithm that adjusts the length of a step and the number of the steps. Sees, for instance, am I exploring? Am I always coming back to the same points? Or am I getting surprised a lot? Because the algorithm, computers are discrete. So what might happen is that I'm here, I'm on the top of the hill, and so I look immediately around me and I expect that if I do a step of 1 meter, right, I should descend of 30 centimeters, right, in physics, right? And then I do the step, but I only check the medial gradient around me. So what might happen is that actually it's a cliff and I fall down. When I'm falling down, if I'm still alive, I assess where I have arrived. And what I have is that the log posterior probability is much, much higher in our case, right, than what I was expecting. In this sense, I've broken the physics of the generator, of the system, and this is a divergence. That's something that we learn to love and despise, right? So this is a bad result. We haven't explored the space in a sensible way. Therefore, we're going to mark these as a divergence, and we're going to move away from those values of step length and number of steps, right? We're going to try a different amount of steps and a different length of step until by far most of our exploration of this space give meaningful results. We're not going back to the same place. We're not breaking the physics of the simulation. Does that kind of make sense? Good. This is what it does. So in JAGs, you get the burn-ins, right? Meaning that you throw away the first steps because you haven't reached a meaningful region of the parameter space. Instead, you have the warm-up, and you really need to throw those away because in those, the parameter of the search are changing constantly, which means that you cannot really compare with what happens after. There was a question somewhere? Yes.
So, like the falling down the cliff analogy.
Yeah.
Would that be like because the step size is too big, so we don't get like the gradient or like how?
Yeah, because the gradient is not constant, right? So if it accelerates too much or it decelerates too much, I might think of going down and then I
The
just
step size.
because of the step size, yes.
Yeah, because if that's just the probability density, then that's just how it is. That's not a bad thing, right?
No, but you want to be able to explore it.
Yeah.
Yes.
Okay, so it's about the step size.
So yes, and if we want to be nitty-picky, it's about the step size and it's about the mathematical formulation of the model. Because sometimes what you have is funnels where in certain region of the posterior space, I think it's actually there. Yes. You want to have big steps up here. In other region, you need very small steps.
Okay, yeah.
And there is no one step size that optimally explores the space. There are ways of going around that, but generally when you have this sort of situation is when you get a lot of divergences. And there are ways of changing the mathematical formulation of the model so that it's mathematically equivalent, but it's sort of stretching in different ways this posterior space.
A smaller step size where there's high probability density.
So here is that because it's changing very fast, so it means you need to have a very small.
Yeah.
Up there, the probability changes relatively slowly, so you want to have big steps. Yes, Martin?
Technically, it counts for divergence when the sampler fails to preserve energy. So they use this physical equation where you have kinetic energy and potential energy.
Yes.
And if their sum is not constant, then you say, okay, something has gone wrong, that's bad. Okay.
Yeah, so I'm in this place in the hill, right? I have a certain potential energy, which depends on how far I am from the ground, from zero.
Density.
That would be my actual log posterior probability. Then you have a kinetic energy, which is I'm going somewhere, right? And given the gradient, right, and my velocity, I expect that at the end of this step, the balance between the kinetic energy and the potential energy will have changed. If I'm going down, the potential energy has decreased and the kinetic energy has increased because I'm picking up momentum. If, after I've done this step, I calculate my log posterior probability and I look at the velocity that I took, if these doesn't match with what I was expecting in the previous step, that's exactly when the difference between the sum of the two is not zero anymore. And then it says the physics is broken, you collapse from the cliff, and therefore you're not exploring this space nicely. There's something that you're doing wrong. Yes.
I'm not sure about the step length.
Yes.
So say you are fitting in like a specific model instead.
Yes.
Has the more steps or iterations. Then are all step size going to be the same length?
Yes.
Even if, like, say, I'm in a very flat part of the.
Yes.
Okay.
In the HMC nuts 2, it's not going to adjust the step size.
Okay, because my intuition would be that if you're in like a steeper incline, then you're going to travel further.
Yes.
You do more steps. How does this set up?
So you do the same amount of steps, actually, but yes. So it's because you have a velocity, right?
Yeah.
So if you have a lot of velocity going on, the momentum, and you do a step like this, it's going to carry you further.
Okay.
Yes, you're right. Then in that sense, it's adjusting to how it's moving. Yeah.
You tune a mass matrix, so you also tune how heavy the ball is.
Yeah.
You tune that for each dimension in probability space. So technically, the step size is the same.
Yeah.
But in reality, it won't be.
Okay.
Because your mass is different in each of the directions.
Okay, makes sense.
And also think of the step size more of the unit of time at which you're measuring.
Yeah.
And given your velocity and acceleration, the actual dimension in space, in absolute distance, will change.
Tricky.
Yeah.
Negative log material, right? Or whatever it is. Then you need to have like more fine grain.
Yes.
Higher time or more fine grain like time resolution.
Yeah, you want to check every millisecond, right?
If you are off. Okay.
Yeah.
Yeah.
Cool. This is very complex, right? And we'll see an alternative for that that's used for prototyping models. But this is what we're going to use as a basic algorithm, as our reference algorithm. It's the best at the moment. Okay. I think I'm actually going to skip these a second. And I'm going to go here. So how do we define a model instead? So there's a bunch of chunks. So you were spoiled and spoiled, rotten by Jags because you could write everything you wanted in every place in the script. Stan says, nope, you need to get your shit together. There are different places where you can put things, and I'm putting some chunks that you need to fill in for the model to run. There's a bunch of stuff, but we're going to start with these three. The first chunk up there is called data, and that's where you specify the format of the data that the model is going to receive. And Stan is a type language, meaning that you need to tell Stan whether the variable X is an integer or a real number or, in principle, strings. It doesn't deal with strings, but you need to specify which kind of variable it is. Then you have a space for parameters, which you should be very familiar with, where you define which parameters have to be estimated and what's the format of the parameters, right? Learning rate is a variable that goes between 0 and 1. Tau, the inverse temperature, is a variable that goes from 0 to potentially plus infinite, unless you try to be sane and you say, well, above 20, I cannot really see any difference in the simulation, so I'm capping it at 20. The model is where you write the likelihood, right, that puts together these variables in the parameters with those variables in the data, and you define the priors, because a Bayesian model is the priors and the likelihood at the same time. So if we want to infer a rate, right, what we have is a sequence of choices, right and left, right, left, etc., etc. I'm representing that as a square because it's discrete, and I'm shading it because it's an observable. And we assume that that sequence of choices is produced by a binomial process of n of 1, that is a Bernoulli process, with a parameter called rate, which often in the literature is called theta, and sometimes we call bias. So I'm putting them all there. And then we can also observe at which trial we are. The bias is a circle, roughly, because it's a continuous variable, and it's as a white background because it's unobserved. Then what we can do is write these as an equation, right? That right is defined as the product of a binomial sampling process with a theta parameter and an n of 1, or a Bernoulli process with a theta parameter. Exactly the same thing. Then what we want to do, since we are Bayesians, is we take the one parameter that we have, that's rate or theta, and we put a prior on that. And for instance, we could say we have no idea to start with. We can put a uniform prior bound at 0 and 1. Do you have better ideas? How do you put a prior on a variable that's constricted between 0 and 1? Yep. This is Josh speaking. I can see you. Yes. Beta distribution. And if we want it roughly uniform, we say that the alpha is equal 1 and the beta is equal 1. Don't you just hate that beta distribution as a beta parameter?
Yeah.
Yes. Okay. Are there other ways that you could think of doing that? Yes. That,
very nice.
yes, good. You could think that Stan is simulating particles that move in a continuous space. So every time you put a boundary, the ball is gonna break the physics and the sampler is not gonna be happy, right? Yeah. So you always need to think in terms of, as much as possible, unlimited spaces. So the beta can assume all sort of values, those parameters that can go from minus infinite to plus infinite, technically. And we want to be able to explore this unlimited Wild West, the Greenland of the new United States, which I'm very against. It was just a joke. Yeah. So what we can do is we can do what we were doing there, right? We can transform a space from 0 to 1 into log odds, right? We could say that we can sample from a normal distribution with a mean of 0 and 1.5, and then put it through the inverse logic. This automatically creates an almost uniform distribution, which is slightly downgrading exact zeros and exact ones. How do I know that? I run it and I visualize it. Right. Good. This is conventions for these kind of notations, but I saw in the couple of assignments that I already sent feedback to that you're already familiar with that. So that's great. This is another notation. Do you know this? This is the Krushky notation. Right? Instead of using the circles and the squares, it uses distributions. Right? The rate is a continuous distribution. The binomial, if you count how many times there's been a right and the left, can be represented like that. And so now we need to turn that into this. So in the data, what would we need to put? Which kind of data are we giving this model, the bias agent? Remember, we're not generating data. We want to take the observable data and infer what rate is. So what is the data that we're seeing? Yes, right. N of trials and sequence of right and left. Good. So the way we write it is we say that data has two variables. One is N and the other is H. I can't remember why I chose H. Let's say Hoya. Right? I think because the first time I wrote this code was head and tails, but I'm gonna blame my Danish. N is specified as int. That is, it's an integer. And it has as a lower boundary 1. Why does it have as a lower boundary 1? Yes?
Because there's no trial 0.
Yeah, if we had no trial, we had no data, right? So the model should throw us error. Then we have an array of integers. What is an array? Well, it's a generic term that can cover vectors and matrices, right? It has length n, that is as many rows as the trials, and it contains an integer. Could we bound the integer? Yes. How would we bound it? Find it.
I mean, between 0 and 1.
Yeah, we could say lower equals 0, upper equal 1. Yes. And that would sort of, if we have the issue that some of our data sets are using 1, 2, and others are using 0 and 1, it's going to throw us an error as soon as we use one of the 1 and 2s, right? Which is good, right? We want to know that. That's why we're constraining things. It gives us tests for free. No, I'm running late, but let's just do the parameters. What should we put in the parameters? Yes?
Data.
Yes, or rate, exactly, rate theta. So theta now is a real number, right? All values between certain boundaries are valid. It has a lower of 0 and an upper of 1. If we get, suddenly the model is trying to estimate a theta that's 3, it will throw an error. It will tell us, with the initial values that I have, I'm generating thetas that are not valid. Go and check. Then we have the model, and I can rush it. Yes. So the model is a Bernoulli distribution that is a binomial distribution with an n of 1, in which the choice is determined by the theta. We write it as target plus equal beta log probability density function, in which we're trying to estimate the parameter theta, given our prior values of alpha equal 1 and beta equal 1, right? This is our prior. Then we have the likelihood, in which we say that we have target plus equal, where we're trying to say that H, the observed behavior, is generated by the Bernoulli log probability mass function with a parameter of theta. There's a couple of things. This is called density. This is called mass. This is a statistical convention. When we talk about continuous distributions, we talk about probability densities. When we talk about discrete distribution of 0 and 1s, right, we talk about mass. It's a bit annoying to have to remember it, but you get over it. The second important point is that we have these weird things. Martin was already mentioning some time ago that you could simply write theta is distributed according to a beta distribution with an alpha of 1 and a beta of 1. And H is distributed according to a Bernoulli with a theta. We could write that. Stan would accept it. That was the old standard. But these days, we write like this to remember an important point. At every step that we do in this posterior space, we need to calculate how probable is the current value given the prior, and add that to how probable is the value given the data. This reminds us that those are two important components that we are calculating at every step. As we get into more complex models, this will multiply. And this helps us keeping an overview of what contributes to the log posterior probability. I think this is just written up in one block with lots of comments, so you can read that through. It's also the same as in the course notes. And then tomorrow, what we're going to do is we're going to start writing your own models in these notation with support. Yes. Thanks for today.